Alright, let's talk about Werner's theory. Alright, so Werner was a Swiss chemist who was the first person to formulate his idea about the structure of coordination compounds. So what he did was he prepared a series of complexes. How did he prepare a series of complexes? By combining cobalt chloride, okay, this is cobalt chloride, with ammonia. He made this complex, and then what he did was, to this mixture of cobalt chloride and ammonia, he started adding excess silver nitrate solution. Alright, to this mixture which he had prepared, he started adding more of this. So what he observed was, some of the chloride ions were precipitated. Okay, now what happens, the reaction is like, some chloride ions will precipitate as AgCl. Okay, the Cl here and the silver, not some of them will precipitate as AgCl. Alright, so he made, and some will be in the solution. Some chloride ions will be in the solution. Only some are going to react with silver. And he made a table like this. The color is yellow. Okay, now color is fine. You don't have to remember. Remember this. Now if at all, the formula is NH3CO, NH3, 6, 3 plus ion. Okay, then he could see that there were 3 chloride ions which he received. So what was the proportion? 1:3 electrolyte. That means for one molecule of this, he got 3 chloride ions. Okay, 3 chloride ions precipitated as silver chloride for one molecule. Alright, now the next color complex is purple. When he observed for the purple complex, the name is something like this: COCl NH3 5 and 2 plus, and this is 2Cl minus, and this was 1:2 electrolyte. Because now if for this colored complex, he did not know what is this formula and all that. We are understanding it. Now you know that for cobalt the oxidation number is 6. So if 5 ammonia 1 chloride will be free, that means 2 chloride will be outside. Alright, so that is how it was, because COCl3 you need to have. Right, so that means 2 chlorides were precipitating out for every molecule. Alright, now next, when the color was green, he saw that there is only 1 chloride ion, so 1:1 ratio. So what should this be? This should be Cl2 and NH3 should be 4, correct? And it will be just 1 plus, because 2 silver ions, 2 plus, right? So this is what it was. And finally, when the color was violet, and he mixed in such a way that he got a violet complex, also it was 1:1. Okay, so the same thing what he observed. Okay, now based on this observation, he proposed his theory, that is called as theory of coordination compounds, and we are going to write the main postulate. So the mixture which you had when it was reacting with silver nitrate, for different color complexes, you used to see different combination or different proportion of chloride ions which were precipitating. It was not the same ratio. Alright, and what he gave was, based on this observation, he gave his theory which says the following things. Okay, now let's write this one by one. First one is, the central metal atom or the ion will have 2 types of valences. Okay, 2 kinds of valences. That is primary valency and secondary valency. Okay, so you can remember, if it is something like this and you have the counter ion like this, you are coming from outside, this is primary and this is secondary. Okay, so just remember that outside is primary, inside is secondary. However you want, you can remember that. Okay, so 2 types of valencies are there for the central atom. Second, the primary valencies, when I say primary valencies, will be ionizable. You know this, correct? So whatever is outside, they will pass all the tests for that particular thing. So they are ionizable completely. Alright, and they are satisfied by negative ions. most of the times. Okay, next. The secondary valencies, if you talk about, they are non-ionizable because they are within the complex, correct? The test, if you do, it will not clear the test because it will not completely be ionizable. It is non-ionizable, okay? And they are satisfied by either negative or neutral, correct? Because inside you can have a neutral also or negative also because metal is positive. Alright, so I hope that part is clear. Next, the fourth one is the secondary valency, whatever we say, that itself is equal to the coordination number of the metal. Okay, the secondary valency is nothing but the coordination number. How many number of ligands are attached? Coordination number of the metal. Okay, the secondary valency itself is the coordination number of the metal, and the primary valency is variable. We have seen that, right? But secondary is fixed for a given metal. Okay, and the secondary valency is also directional. Why? Because you have seen geometry based on the coordination number. You can have a specific geometry, square, planar, octahedral, tetrahedral and all that, right? So it is directed in space and it gives you a particular geometry, shape is given, that is decided by the secondary valency. Alright, now simple words, just remember secondary valency is coordination number, and primary valency is nothing but the oxidation number. Okay, primary valency is the oxidation number of what? The central metal. This is all you need to remember. Okay, central atom, metal atom, the secondary valency of that atom is nothing but the coordination number. Secondary valency is non-ionizable. Primary valency is related to the counter ion, that is giving you the oxidation state or the oxidation number. Let us write the drawbacks. Okay, so these were the first theory what he gave. Okay, drawback of is that he could not understand why only certain compounds show complexes. Why there is complex ion formed only in certain compounds? He could not explain that. Second, he could not explain why the secondary valencies is showing the directional property. How is it getting shape? Okay, for this compound, why is the shape octahedral? For this, why it is square planar? He could not explain that. Alright. He also could not explain why some are paramagnetic and why some are diamagnetic. That also he could not explain. Okay, now these there are three main things which he could not explain in his theory, but he did a decent job in telling you the basic information that whatever is inside the coordination entity, that is the secondary valency, it is non-ionizable and that will be the coordination number. Whatever is written outside the coordination entity, that is the counter ion, that is the primary valency and that is ionizable and that will give you the oxidation state. Okay, so moving forward, the next theory which we need to know, which was an improvement over Werner's theory, was the VBT, valence bond theory. Okay, so let us understand the points of VBT. Okay, so VBT is based on there are some assumptions which it is based on. The first one is you have the central metal atom. The central metal atom provides vacant orbitals for the formation of complexes. Okay, see what is actually happening. You have a central metal atom and the ligands are approaching it, and the ligands are giving ligands have lone pair of electrons. They give their lone pair of electrons and form the bond. Finally, when the ligands are approaching and a bond is formed, the electrons which are donated by the ligands should be occupied in some orbital. They cannot be in random space. So who provides that vacant orbital? The central metal atom. Alright. Next, the number of vacant orbitals is equal to the number of vacant orbitals which are provided by the central atom should be equal to the coordination number of that. Okay, now coordination number is generally fixed. Like I said, the secondary valency is fixed, coordination number is fixed for a given thing, right? So it is nothing but the coordination number. All right. Okay. Now the third, the vacant orbitals which are provided by the metal for the ligands to occupy, for the electrons of the ligands to be occupied. So these vacant orbitals, they undergo hybridization, and this results in the formation of equal energy orbitals. Okay. The fourth one, the now you have hybrid orbitals. The central metal is having hybrid orbitals now. These hybrid orbitals overlap with the orbitals of the ligand. Okay, and when the electron is overlapping means what? There is sharing and they form coordinate bonds. Okay, next, the fifth one, the geometry. This theory is good in a way because it is able to explain the geometry. So the shape or the geometry of the complex, it depends on the number of hybrid orbitals, how many hybrid orbitals, and also on the type of hybridization. Okay, I will list it. Next, if at all the complex contains, after hybridization and everything, if the complex contains unpaired electrons in the shell, okay, then it is what we call as paramagnetic. It shows magnetic behavior. Okay, and if there are no unpaired, everything is paired, that is what we call as diamagnetic. No magnetic property is shown. Okay, now you just have to know this is the theory. All right, so number of vacant orbitals, they undergo hybridization. So when a ligand attains, there is overlap, there is bond formation, and the shape depends on how many types of orbitals are there and the type of hybridization. And if it's unpaired, paired is dia. Okay, now for coordination number 4, okay, this is the coordination number, and you don't have for 5. Type of hybridization, if it is sp3, there are two types for 4. Okay, one is mixing with 3 p orbitals, or dsp2, the d orbital and s orbital and the p orbital, d orbital of the previous shell, s and p of the next shell. Okay, so there are two kinds of hybridization possible for coordination number 4, that is sp3 and dsp2. So if it is sp3, then the shape will be tetrahedral. If it is dsp2, then it is square planar. Tetrahedral is something like this, right? So you have like this, and something like this. It's like a square based pyramid. You can think there is a square wherein the metal atom and the 3 ligands occupy, and one ligand here, and all of them they join. That is tetrahedral. Whereas square planar, when we say you have the central metal atom, it is something like this, and they occupy the 4 ligands occupy the square. It's like a plane. At the center there is this, and 4 sides you have a ligand. Okay, now examples if you want. This will be, and you don't have to remember this. This is NiCl 2 minus. You see coordination number 4. You have to write it in brackets anyways. And this is NiCN4 2 minus. This is Cl and this is Cn. Okay. Now we will understand why this is square planar and tetra in a while. And if it is 6, it can have two possibilities, D2sp3 and sp3d2. Okay. This, both the shape is octahedral. Octahedral is like the metal at the center, and the 4 ligands will be a square planar, and the other 2, because there are 6 ligands, they will occupy. It is like a square based pyramid, but on top and bottom, something like that. Okay, so both of them will have octahedral. There's a difference. Example for this will be CONH36 to cobalt is 3 plus, and COF6 3 minus. Okay, so this is what it is. You will understand this when we go into the details. Alright, so let us now, generally, now you have learned it a different way, but this is talking about shape, and that is the explanation it gives, but it will not talk about why it is this, okay, or why there is pairing and unpairing, how it is formed. So in the theory, they'll generally give you that it is para or dia. Okay, but I will not do questions now. We will combine this with the CFT and then we will understand it. So I will not take a question here. First we will do CFT and then we will take this up. Okay, because otherwise it will be a little confusing for you. Alright, so now let us talk about the limitations of VBT. Okay, limitations is that it is not accounting for the color. Some compounds show color, blue color, pink color. It is not accounting for that. It's not explaining that. Okay, it is not able to explain the thermodynamic or kinetic stability. Okay, why something is thermodynamically stable? You know about thermodynamic aspect or kinetic aspect of it. Okay, why something is fast, some react fast, some react slow. All that stabilities it is not able to explain. Third, it is not talking about main thing. This is the failure. Okay, why in some cases there is pairing and some cases there is unpairing. Correct? And it is not having the concept of weak and strong ligands. Okay, this comes actually in CFT. But finally, when you are asked a question to write everything, if you know the knowledge of CFT, you will be able to identify, and once it is there, you can understand what is happening everywhere. Right? So that's fine. And the last one is, it is not giving you the type of magnetic data, what kind of magnetism, para, dia and all that. Okay, so it is definitely an improvement in the case that it at least based on the type of hybridization, if you know the coordination number, you will be able to find the kind of hybridization once you know the oxidation number and all that. And once you identify the type of hybridization, you are able to tell the shape of it. But still you cannot talk about these two things. Okay, and this was given in the CFT. Okay, so I'll cover up CFT in a separate video.